In today's video, let's use serial bus servos with a Raspberry Pi. As usual, you will see a circuit, source code and several working demos. I will use LX-16A servo motors. This servo model is in the robot that you might have seen on this channel. In addition to that, you will get Python modules that allow smooth rotation of servo motors. The link will be in the description. If you like the libraries and tutorials I am creating, please subscribe and support me through a link in the description. Now let's begin. This is the circuit drawing that includes all necessary components to control serial bus servos with Raspberry Pi. One of these components is this small white board that is called the BusLinker. The BusLinker has a micro USB connector that should be connected to an USB port of Raspberry Pi, and the BusLinker should be also connected to an external power source. These motors need a power source in the range between 6 and 8 volts. I think it is possible to use lower voltage, for instance 5 volts, but it's not guaranteed if these motors will work, and their performance will be much lower. These motors come with Molex cables that you can use to connect them to the BusLinker and to between themselves. These Molex cables consist of 3 wires. These wires correspond to pins of these bus servos, which are ground, voltage, and the signal. What is convenient about these servo motors is that you can combine them into a chain like you see in this drawing. It is useful in robotics. For instance, in a robot you can have a leg or an arm that could be long, and you don't have to extend cables from a board to each of the servo motors. You can put the servo motors in the joints and connect one to another. That's all about the circuit. Now let's try some source code examples in Python for Raspberry Pi. These examples require this LX-16A module. It is created by another person, not by me. The references you can find in my repository. This is the repository with all examples that we are going to discuss in this video, and it also includes a short documentation with the most useful and frequently used methods of LX-16A class. Let's look at the first thing that we need to do to work with LX-16A servo motors with the BusLinker. We need to initialize that BusLinker, and since it is a USB serial device in Linux or in Mac, you will need to use this device name. For instance, this is the typical device name in Raspberry Pi OS. In a different Linux distribution or in Mac, it will be different. To identify the device name, use the following command: ls-dev-tty**. It will show all serial devices connected to your computer, including virtual devices, and here you see there is a device named TTY USB 0, which is typical for Raspberry Pi. If I detach the BusLinker from the USB port and if I run this command again, you can see that there is no USB 0 device anymore. If I put it back again and run this command again, you can see the device again is here. So that's how you can identify device on any computer, whether it is Linux, any distribution, or Mac. In Windows, I believe this approach should be different. Perhaps you need to use the device manager, but I'm not an expert on Windows, so I think you can figure out what device to put here yourself. One more thing that we need to do before running examples that we're discussing in this video, we need to install pyserial package. In Raspberry Pi OS, it could be done using this command, sudo apt install python 3 serial. This package is already in my system, so the command just says that it's already installed. If you are using virtual environments, use another command, this one. But for simplicity, I'm not using virtual environment in my installation, so it's just for your reference. So let's continue with our example. The first thing I need to do after initializing the BusLinker is to create instances of LX-16A class. I need to create motor objects. In my case, I'm using IDs 1 and 2 for my servo motors. They all have IDs, we will discuss it later. Then I enable torque and switch them to servo mode. These commands are not necessary. It could be that you disabled torque previously or switched them to motor mode, but by default the torque will be enabled and they will be in servo mode. I use the main loop to repeat rotation of servo motors. You will see it in physical system demonstration, but here I will tell how it works. First, I get physical angle. This method just reads the current angle at which my motor is at which my motor positioned at this moment, and this angle could be between 0 and 240 degrees. Sometimes this function returns like slightly negative, slightly below 0 angle, or slightly more than 240 degrees, so be careful. You cannot directly use this value to command later the motor to go to that angle. So if it's just below 0, you need to adjust it and set it to 0. Then I use this command, move. It commands the motor to go to the angle I'm providing here. It will the value is a float between 0 and 240 degrees. Okay, and I repeat this cycle. You will see it in the physical system demonstration. So that's how it works in real life. You see the motor moves from 0 to 240 degrees, but you may notice that this motion is quite abrupt. In the next example, let's use a sinusoidal oscillator to make the motion of our servo motor smooth, so it starts and stops its motion smoothly. How to achieve that? First, to initialize the class, I created class Sine Oscillator. To initialize that class, you need to provide an instance of your servo motor. Then in the start method you provide the maximum angle, which will be the double of your amplitude, and the number of oscillations. So for instance, if the maximum angle is 240 degrees, then it will oscillate with amplitude 120 degrees. The number of oscillations is how many times to perform that oscillation. Okay, and in the update method, it will use a sine function here. This function will also not be just a sine function, but it will include this amplitude. You can see the maximum angle divided by 2, and it will add this angle divided by 2. So, and then it will, using this function, it will calculate an intermediate angle, and in the update function, the class, the object, will use this command move that we have seen in the simple servo example. It will move frequently, every 50 milliseconds. It will command the motor to move toward that intermediate angle. Its running method, it just verifies if this oscillation is running or finished. So in my program, I again initialize two motors, enable torque, switch them to servo mode if they are not. Then I command them to go to the position 0 and start my initialize my oscillator, and in the main loop, if it's not running, I command it to begin to perform 2 oscillations, and I change my amplitude. So the maximum angle, I decrease it from, initially it was 240 degrees, I decrease it by 90 degrees. You will see how it works in the physical system demonstration in a couple of seconds. So then after oscillation starts, I just repeat this cycle. So let's run this program and see how it works. This is how oscillation works. It starts from the maximum amplitude, and after a couple of oscillations the amplitude decreases, but the pattern, the sinusoidal pattern, stays the same. In the next example, we are going to print some information, read some parameters of the servo motor and print them. This example again consists of initialization, these lines of code, then these two functions just to print some fancy stuff, and then these are methods that we are interested in. The first one is get Vin. It's to get voltage of the servo motor, and it will be in millivolts. Get temp is to read temperature. It will be in degrees Celsius. Then is motor mode method returns boolean, and if motor is in motor mode, it will return true, otherwise it will return false. And this motor mode allows our servo motor to rotate constantly 360 degrees without be able to stop and without be able to go to a certain position. Sometimes that could be useful. You just provide speed of rotation. We will discuss it later in one of other examples. Is torque enabled method returns true if torque is enabled, and if yes, then you cannot easily turn the motor with your hand because it will resist this rotation. Is LED power on just indicates if internal LED of the motor is on or off. You can see how it looks in real life. I switch this LED on and off here in the program. Okay, and of course I print everything in the command line. So let's go and see how it works if we try to run this program. To run the program on Raspberry Pi, I will use this command. And you can see it prints MixRobot logo and all parameters that we want. Motor mode, torque, LED, voltage and temperature. Our next example is called set ID. It is used to set the ID of a servo motor. LX-16A servo motors come with the default ID of 1, but to work with them in your project, because you are going to use several motors, you cannot use the same ID for all of them. And this method, setID, just sets the ID of a servo motor, and this number should be an integer number in the range 1 to 253. You need to set this ID only once. Even if you turn off power after that, the motor will save that ID into its permanent memory, and that's all. The next time you just address this motor by that new ID. The next example is called Smooth Motor, and it provides Smooth Motor class that performs beginning and stopping of rotation of our servo in motor mode smoothly without abrupt motion. So let's discuss how it works. In the constructor method init, we need to provide the instance of our servo motor. In start method, we need to set the target speed. It will achieve that speed after certain time, and in stop method we don't need to provide anything. It just slowly stops the rotation of the motor. In motor mode, our servo is rotating at constant speed without stopping at certain angle, and that rotation is just like a regular motor. Could be 360 degrees. So in the update method, it's actually the most important method, where all easing in and easing out happens. So here, every 25 milliseconds, the speed is recalculated, and the step is 25 or minus 25, depending on what direction of rotation we have and what we're doing, starting or stopping. The maximum speed is 1000 in one direction, and in the opposite direction it's minus 1000. So the target speed could be anything between minus 1000 and 1000. So this is a linear function. We increase this speed linearly or decrease linearly. In our program, we again initialize everything. We create instances of our motors with IDs 1 and 2, enable torque if it's disabled, and set them to motor mode, initially with the speed 0, so that they don't immediately start rotating. Then we begin our smooth motor, but it will not do anything until we call the update method in the loop. Every time we call that method, it recalculates the speed of rotation, and when it reaches its target speed, it will just continue rotating at that speed. After 5 seconds, here we specify that we stop our motors. Then we just, every time we also check whether they are running. If they are stopped, We change direction of rotation and by using this minus sign, and we begin rotation in the opposite direction. So let's look how it works in real life. Let's run the program. So you see our motors slowly start rotating, slowly stop rotating. It's not actually too slowly, but it's not an abrupt motion. You can play with step, with target speed, with all parameters, with time interval, but you get the idea. The last but not the least, and the best example, is called smooth servo. In this example, I provide class smooth servo that will start rotation of our servo in servo mode slowly, easing in, and stop its rotation, easing out also smoothly. In this example, our servo will be able to go from any its current angle to any its target angle. So basically it's almost the same as move command, but the beginning and stopping will be done without abrupt motion. So in the constructor init method, I just provide the instance of my servo motor. In start method, I give the target angle, and in this update method, I recalculate this angle, this intermediate angle to which my motor wants to go at any certain time. How it works, let me show you the graph of a function that it uses. So you see that, for instance, we want to go from 0 to 1. You can see that when I start moving from 0, this part of the graph is like slowly increasing, then goes through the middle point, and here the speed is almost constant, then it slowly decreases. So that's how it will work in our program. It will ease in and ease out. I can use any values for T and S, which represent target and starting position. For instance, it could be 0 and for instance, it could be the opposite, from 1 to 0. We go from 1 to 0. It could be, we go from 0 to 3. So the pattern is always the same. That's how it works. You will see it in the physical system demonstration. Let's go back to our code. So I use this function in my code. I calculate intermediate angle. I command my servo motor to go to that angle every 50 milliseconds. And in the main program, I initialize everything. I initialize servo motors with IDs 1 and 2, enable torque, switch them to servo mode, and create instances of smooth servo class. Then in the main loop, I always call this update method. If any of our motors is not running, I start its movement with providing target angle. In my example, they simply go from 0 to 120, then to 240 degrees, and then go back. You can create any logic, use any angles you want. It's just an example. So let's see how it works in real life. Let's run this program. you can see that the beginning of its movement is quite not abrupt, it's easing in, and when it stops it's easing out. So exactly as we see on the graph, this pattern. This kind of pattern is important for robotics, because in robotics we want that motion should be smooth, not abrupt, because otherwise the robot can fall or damage something, damage itself. So we want to avoid that. If you like these videos that I'm creating and these code examples, please support me, the link in the description of the video, and subscribe to this channel. Thank you for watching this video. See you next time.